High-speed rail is a type of rail transport that operates significantly faster than traditional rail traffic, using an integrated system of specialized rolling stock and dedicated tracks. The first such system began operations in Japan in 1964 and was widely known as the bullet train. High-speed trains normally operate on standard-gauge tracks of continuously welded rail on grade-separated right-of-way that incorporates a large turning radius in its design. Many countries have developed high-speed rail to connect major cities, including China, France, Germany, Italy, Taiwan, Turkey, South Korea and Spain. While high-speed rail is usually designed for passenger travel, some high-speed systems also offer freight service. For instance, the French mail service La Poste owns a few special TGV trains for carrying postal freight. Definitions. Multiple definitions for high-speed rail are in use worldwide. The European Union Directive 96/EC, Annex 1 defines high-speed rail as a set of three elements with precise criteria. Infrastructure, track built specially for high-speed travel or specially upgraded for high-speed travel. Maximum speed limit, minimum speed of 200 km/h on lines specially built for high speed and 250 km/h on existing lines which have been specially upgraded. This must apply to at least one section of the line. Rolling stock must have a maximum speed of at least 200 km/h to be considered high speed. Operating conditions, rolling stock must be designed alongside its infrastructure for complete compatibility, safety and quality of service. The International Union of Railways prefers to use definitions, because they consider that there is no single standard definition of high-speed rail, nor even standard usage of the terms. They make use of the European EC Directive 96/48, stating that high speed is a combination of all the elements which constitute the system, infrastructure, rolling stock and operating conditions. Some nations have domestic standards which may vary from the international ones. The International Union of Railways states that high-speed rail is a set of unique features, not merely a train traveling above a particular speed. Many conventionally hauled trains are able to reach 200 km/h in commercial service but are not considered to be high-speed trains. These include the French SNCF Intercity Copyright S and German DBIC. History. Railways were the first form of rapid land transportation and had an effective monopoly on passenger traffic until the development of the motor car and airliners in the early mid-20th century. Speed had always been an important factor for railroads and they constantly tried to achieve higher speeds and decrease journey times. Rail transportation in the late 19th century was not much slower than non-high-speed trains today and many railroads regularly operated relatively fast express trains which averaged speeds of around 100 km/h. Early research. First experiments. High-speed rail development began in Germany in 1899 when the Prussian State Railway joined with 10 electrical and engineering firms and electrified 72 kilometers of military-owned railway between Marienfelde and Zossen. The line used three-phase current at 10 kV and 45 Hz. The Van der Zijden Company of Deutz, Cologne built two rail cars, one fitted with electrical equipment from Siemens Halske, the second with equipment from LG Marine Electricity Currency TS Gesellschaft, that were tested on the Marienfelde-Zossen line during 1902 and 1903. On October 23, 1903, the S&H-equipped rail car achieved a speed of 206.7 km/h and on October 27 the AEG-equipped rail car achieved 210.2 km/h. These trains demonstrated the feasibility of electric high-speed rail. However, regularly scheduled electric high-speed rail travel was still more than 30 years away. Early German high-speed network. On May 15, 1933, the Deutsche Reichsbahngesellschaft Company introduced the diesel-powered Fliegende Hamburger in regular service between Hamburg and Berlin, thereby establishing the fastest regular service in the world, with a regular top speed of 160 km/h. This train was a streamlined multi-powered unit, albeit diesel, and used Jacobs bogies some 47 years before the advent of the TGV. Following the success of the Hamburger line, The steam-powered Henschel Wegman train was developed and introduced in June 1936 for service from Berlin to Dresden, with a regular top speed of 160 km per hour. Further development allowed the usage of these Fliegend and Saar 1/4 GE on a rail network across Germany. The diesel Schnelltreibwagen nets had been in the planning since 1934, but it never reached its envisaged size. And in August 1939, shortly before the breakout of the war, all high-speed service stopped. The American streamliners, on May 26, 1934, 1 year after Fliegend to Hamburger introduction, the Burlington Railroads set an average speed record on long distance with their new streamlined train, the Zephyr, at 124 km per hour with peaks at 185 km per hour. The Zephyr was made of stainless steel, and like the Fliegend to Hamburger, was diesel-powered, articulated with Jacobs bogies, and could reach 160 km per hour as commercial speed. The new service was inaugurated at the end of year, November 11, 1934, between Kansas City and Lincoln, but at lower speed than the record, with an average speed of 74 km per hour. In 1935, Milwaukee Road Company introduced the morning Hiawatha service, hauled at 160 km per hour by steam locomotives. These were the last high-speed trains to use steam power. In 1936, the Twin Cities Zephyr entered service, from Chicago to Minneapolis, with an average speed of 101 km per hour. The Italian electric and the last steam record, the German high-speed service was followed in Italy in 1938 with an electric multiple-unit ETA 200, designed for 200 km per hour, between Bologna and Naples. It too reached 160 km per hour in commercial service, and achieved a world mean speed record of 203 km per hour near Milan in 1938. In Great Britain in the same year, the streamlined steam locomotive Mallard achieved the official world speed record for steam locomotives at 125.88 mph per hour. The external combustion engines and boilers on steam locomotives were large, heavy and time-consuming to maintain, and the days of steam for high speed were numbered. The birth of Talos system, in 1945, a Spanish engineer, Alejandro Goicoechea, developed a streamlined articulated train able to run on existing tracks at higher speeds than contemporary passenger trains. This was achieved by providing the locomotive and cars with a unique axle system that used one axle set per car end, connected by a wide bar coupler. Amongst other advantages, the center of mass was only half as high as usual. This system became famous under the name of Talo, and for half a century was the main Spanish provider of high-speed trains. The first very high-speed records. In the early 1950s, the French National Railway started to receive their new powerful CC-70-100 electric locomotives, and began to study and evaluate running at very high speeds. In 1954, the CC-70-121 hauling a full train achieved a record 243 km per hour during a test on standard track. The next year, two specially tuned electric locomotives, the CC-70-107 and the prototype BB-9001, broke previous speed records, reaching respectively 320 km per hour and 331 km per hour, again on standard track. For the first time, 300 km per hour was surpassed, allowing the idea of regular very high-speed services to be developed. New engineering studies began for this purpose. Especially, during the 1955 records, very dangerous hunting oscillation, the swaying of the bogies which at high speed leads to dynamic instability and potential derailment, was discovered, which led to the use of yaw dampers to solve this problem, enabling safe running speeds above 300 km per hour today. Important research was also made about current harnessing at high speed by the pantographs, that was solved 20 years later by the Saar copyright bull on TGV's prototype. Breakthrough, the Shinkansen. Japanese research and development, with some 45 million people living in the densely populated Tokyo to Osaka corridor, congestion on road and rail became a serious problem after World War II, and the Japanese government began thinking seriously about a new high-speed rail service. Japan in the 1950s was a populous, resource-limited nation that for security reasons did not want to import petroleum, but needed a way to transport its millions of people in and between cities. Japanese National Railways engineers then began to study the development of a high-speed regular mass transit service. In 1955, they were present at the Lille's Electro-Technology Congress in France, and during a 6-month visit, the head engineer of JNR accompanied the deputy director Marcel Tessier with the DETE. JNR engineers returned to Japan with a number of ideas and technologies they would use on their future trains, including alternating current for rail traction, and international standard gauge. The first narrow-gauge Japanese high-speed service, in 1957, the engineers at the private Odakyu Electric Railway in Greater Tokyo area launched the Odakyu 3000 series SE EMU. This EMU set a world record for narrow-gauge trains at 145 km/h, giving the Odakyu engineers confidence they could safely and reliably build even faster trains at standard gauge. The original Japanese railways generally used narrow gauge, but the increased stability offered by widening the rails to standard gauge would make very high-speed rail much simpler, and thus standard gauge was adopted for high-speed service. A new train on a new line, the new service, named Shinkansen, would run on new, 25% wider standard gauge, continuously welded rails between Tokyo and Osaka using new rolling stock, designed for 250 km/h. However, the World Bank, whilst supporting the project, considered the design of the equipment as unproven for that speed, and set the maximum speed to 210 km/h. After initial feasibility tests, the plan was fast-tracked and construction of the first section of the line started on April 20, 1959. In 1963, on the new track, test runs hit a top speed of 256 km/h. 5 years after the beginning of the construction work, in October 1964, just in time for the Olympic Games, the first modern high-speed rail, the Takeda Shinkansen, was opened between the two cities. The first Shinkansen trains, the Zero Series Shinkansen, built by Kawasaki Heavy Industries, are Euro in English often called bullet trains, after the original Japanese named Angon Res or Euro outclassed the earlier fast trains in commercial service. They ran the 515 km distance in 3 hours 10 minutes, reaching a top speed of 210 km/h and sustaining an average speed of 162.8 km/h with stops at Nagoya and Kyoto. A great success, but the speed was only a part of the Shinkansen revolution. The Shinkansen offered high-speed rail travel to the masses. The first bullet trains had 12 cars and later versions had up to 16, and double-deck trains further increased the capacity. After 3 years, more than 100 million passengers had used the trains, and the milestone of the first 1 billion passengers was reached in 1976. In 1972, the line was extended a further 161 km, and further construction has resulted in the network expanding to 2,387 km as of March 2013, with a further 776 km of extensions currently under construction and due to open in stages between March 2015 and 2035. The cumulative patronage on the entire system since 1964 is over 10 billion, the equivalent of approximately 150% of the world's population, without a single train passenger fatality. Since their introduction, Japan's Shinkansen systems have been under relentless development, not only increasing line speeds. Dozens of models have been produced, addressing diverse issues such as tunnel boom noise, vibration, aerodynamic drag, lines with lower throughput, earthquake and typhoon safety, braking distance, problems due to snow, and energy consumption. Revival in Europe and North America. First demonstrations at 200 km/h. In Europe, high-speed rail began during the International Transport Fair in Munich in June 1965, when Driver Ehring, the director of Deutsche Bundesbahn, performed 347 demonstrations at 200 km/h between Munich and Augsburg by DB Class 103 hauled trains. The same year the Your Copyright Row train, a French hovercraft monorail train prototype, reached 200 km/h within days of operation. Le Capitole, after the success of the Japanese Shinkansen in 1964, at 210 km per hour, the German demonstrations up to 200 km per hour in 1965, and the proof of concept jet-powered or copyright road train, SNCF still ran its fastest trains at only 160 km per hour. In 1966, French Infrastructure Minister Edgar Pisani consulted engineers and gave the French National Railways 12 months to raise speeds to 200 km per hour. The classic line Paris-Toulouse was chosen, and fitted, to support 200 km per hour rather than 140 km per hour. Some improvements were set, notably the signals system, development of onboard in-cab signaling system, and curve revision. The next year, in May 1967, a regular service at 200 km per hour was inaugurated by the Tila capital between Paris and Toulouse, with specially adapted SNCF Class BB 9200 locomotives hauling classic UIC cars, and a full red livery. At the same time, the copyright road train prototype 02 reached 345 km per hour on a half-scale experimental track. In 1969, it achieved 422 km per hour on the same track. On March 5, 1974, the full-scale commercial prototype or copyright road train I-80HV, jet-powered, reached 430 km per hour. American Metroliner trains achieved 200 km per hour. In the United States, immediately following the creation of Japan's first high-speed Shinkansen, U.S. President Lyndon B. Johnson, as part of his Great Society infrastructure building initiatives, asked the U.S. Congress to devise a way to increase speeds on American railroads. The Congress delivered the High-Speed Ground Transportation Act of 1965, which passed with overwhelming bipartisan support and helped to create regular Metroliner service between New York City and Washington, D.C. The new service was inaugurated in 1969, at speeds reaching 200 km per hour and averaging 145 km per hour along the route, faster than even ASLA Express trains operated between the cities of New York and Washington in 2012. The HST, a diesel high-speed train at 200 km per hour, Great Britain followed Japan, France and US in 1976 with the introduction by British Rail of a new high-speed service, able to reach 200 km per hour, hauled by the Intercity 125 diesel-electric train sets, under the brand name of high-speed train. It was the fastest diesel-powered train in regular service in the world, and it outclassed its 100 mph forerunners, in speed and acceleration. Like the Shinkansen, and future TGV, the train was built as a reversible multi-car set, having driving power cars at both ends, and a fixed formation of passenger cars between them. Journey times were reduced, sometimes by an hour on the East Coast Main Line, and passenger numbers soared. Europe at 200 km per hour. The next year, in 1977, Germany finally introduced a new service at 200 km per hour, on the Munich-Augsburg line. That same year, Italy inaugurated the first European high-speed line, the Direttissima between Roma and Florence, designed for 250 km per hour, but used by FSE 444 hauled train at 200 km per hour. This year also saw the abandonment for political reasons of the copyright road train project, in favor of the TGV. The French TGV. Active research. Following the 1955 records, two divisions of the SNCF began to study high-speed services. In 1964, the DETMT planned the use of gas turbines. A diesel-powered rail car is modified with a gas turbine, and is called TGV. It reached 230 km per hour in 1967, and served as a basis for the future turbo train and the real TGV. In the same time, the new SNCF Research Department, created in 1966, was studying some projects, especially a project codenamed CO3 Railways possibilities on new infrastructure. The gas turbine. In 1969, the CO3 project was transferred to the public administration while a contract with Alstom is ratified for the building of two gas turbine high-speed train prototypes, that will be named TGV-001. The prototype consisted of an undividable set of 5 cars and 2 power cars at both ends, each power car powered by 2 gas turbine engine. The notable particularity of the set is the use of Jacob's bogies, shared by two cars, that reduce drag and increase safety. The next year, in 1970, the DETMT's turbotrain, gas turbine-powered multiple elements, designed for 200 km per hour but used at 160 km per hour, began operations on Paris-Cherbourg line. It allowed to experiment future TGV services, especially regular high-rate schedules, shuttle services, etc. The CO3 project, in 1971, the CO3 project, now known as TGV Sudist, was validated by the government, against the Bertins Aerotrain. Until this date, there was a rivalry between the French Land Settlement Commission, supporting the copyright road train, and the SNCF and its ministry, supporting conventional rail. The CO3 project included a new high-speed line between Paris and Lyon, with new multi-engine trains running at 260 km per hour. At that time, the classic Paris-Lyon line was already congested and a new line was required. This busy corridor, not too short nor too long, was the best choice for the new service. Turnaround, electricity. The 1973 oil shock substantially increases oil prices. In the continuity of the de Gaulle energy self-sufficiency, and nuclear energy policy, a ministry decision switched the future TGV from now costly gas turbine to full electric energy in 1974. An electric rail car named Tsar Copyright Ballon was developed for testing at very high speeds, reaching a speed of 306 km per hour. It was used to develop pantographs capable of withstanding speeds of over 300 km per hour. The TGV, the first service above 250 km per hour, after intensive tests with the gas turbine TGV-001 prototype, and the electric Tsar Copyright Ballon, in 1977, the SNCF placed an order to the Groupe Alstom Franco Rail MTE for 87 TGV Sudist train sets. They used the TGV-001 concept, with a permanently coupled set of 8 cars, sharing Jacob's bogies, and hauled by 2 electric power cars, one at each end. In 1981, the first section of the new Paris-Lyon high-speed line was inaugurated, with a 260 km per hour top speed soon after. With a far greater top speed, a new dedicated high-speed line, and a complete compatibility with existing old lines, the TGV offered the ability to join every city in the country, using alternatively standard and high-speed line, in a shorter time than ever. After the introduction of the TGV on some routes, air traffic on these routes decreased, or even disappeared. At the same time, the TGV made history with its multiple, highly publicized speed records, in 1981 with a record at 380 km per hour, in 1990 at 515 km per hour, and then in 2007 at 574 km per hour. Evolution in Europe. Following the French TGV, in 1991 Germany was the second country in Europe to inaugurate a high-speed rail service, with the launch of the Intercity Express on the new Hanover ZBURG high-speed railway, operating at a top speed of 280 km per hour. The German ICE train was similar to the TGV, with dedicated streamlined power cars at both ends, but a variable number of trailers between them. Unlike the TGV, the trailers had 2 conventional bogies per car, and could be uncoupled, allowing the train to be lengthened or shortened. This introduction was the result of 10 years of study with the ICE-V prototype, which broke the world speed record in 1988, reaching 406 km per hour. In 1992, just in time for the Barcelona Olympic Games and Seville Expo 92, the Madrid-Seville high-speed rail line opened in Spain with 25 kV AC electrification, and standard gauge, differing from all other Spanish lines which used Iberian gauge. This allowed the AVE rail service to begin operations using Class 100 train sets built by Alstom, directly derived and designed from the French TGV trains. The service was very popular and development continued on high-speed rail in Spain. In 2005, the Spanish government announced an ambitious plan, envisioning that by 2020, 90% of the population would live within 50 km of a station served by AVE. Spain began building the largest HSA network in Europe. As of 2011, 5 of the new lines have opened and another 2,219 km were under construction. Evolution in North America. In 1992, the United States Congress authorized the Amtrak Authorization and Development Act to focus on Amtrak's service improvement on the segment between Boston and New York City of the Northeast Corridor. The primary objectives were to electrify the line north of New Haven, Connecticut and replace the then 30-year-old Metrolinas with new trains to achieve shorter travel time. Amtrak started testing 2 trains, the Swedish X2000 and the German ICE-1, in the same year along its fully electrified segment between New York City and Washington, D.C. The officials favored the X2000 as it had a tilting mechanism. However, the Swedish manufacturer never bid on the contract as the burdensome United States railroad regulations required them to heavily modify the train, resulting in added weight among other things. Eventually, a custom-made tilting train derived from TGV, manufactured by Alstom and Bombardier, won the contract and was put into service in December 2000. The new service was named ASLA Express, and linked Boston, New York City, Philadelphia, Baltimore, and Washington, D.C. The service did not meet the 3-hour travel time objective, between Boston and New York City. The time was 3 hours and 24 minutes as it partially ran on regular lines, limiting its average speed, with a maximum speed of 241 km per hour being reached on a small section of its route through Rhode Island and Massachusetts. There have been many studies of high-speed rail in Canada, mostly for the densely populated Windsor, Toronto, Montreal-Quebec City corridor. Most recently, the Ontario Minister of Transport Glenn Murray announced plans to develop HSA between Toronto and London, Ontario. Expansion in East Asia. For 4 decades from its opening in 1964, the Japanese Shinkansen was the only high-speed rail service outside of Europe. In the 2000s, a number of new high-speed rail services started operating in East Asia. The South Korean KTX. In South Korea, Korea Train Express services were launched on April 1, 2004, on the Seoul-Busan corridor, Korea's busiest traffic corridor, between the 2 largest cities. In 1982, it represented 65.8% of South Korea's population, a number that grew to 73.3% by 1995, along with 70% of freight traffic and 66% of passenger traffic. With both the Gyeongbu Expressway and Koral's Gyeongbu line congested as of the late 1970s, the government saw the pressing need for another form of transportation. Construction began on the high-speed line from Seoul to Busan in 1992, with the first commercial service launching in 2004. Top speed for trains in regular service is currently 305 km per hour, though the infrastructure is designed for 350 km per hour. The initial rolling stock was based on Alstom's TGV Ra copyright So, and was partly built in Korea. The domestically developed HSA 350X, which achieved 352.4 km per hour in tests, resulted in a second type of high-speed trains now operated by Korail, the KTX Sankan. The next-generation KTX train, HEMU 430X, achieved 421.4 km per hour in 2013, making South Korea the world's 4th country after France, Japan, and China to develop a high-speed train running on conventional rail above 420 km per hour. The Chinese CRH. State planning for China's high-speed railway began in the early 1990s, and the country started construction of its first high-speed rail line, the Qinhuangdao Euro-Shenyang Passenger Railway, in 1999, which subsequently opened in 2003 with a design speed of 200 km per hour. The original goal of the Chinese Ministry of Railways was to research and develop domestic technology to reach a world standard. The new high-speed rail line was used to test several Chinese-developed prototypes. Although they were successful at creating a train set that operated at 300 km per hour, the trains performed poorly in regular service. Realizing that domestic high-speed technology was not sufficiently developed, the MOA purchased high-speed trains from French, German, and Japanese manufacturers with technology transfer contracts to improve its ability to build high-speed trains. In 2007 the first high-speed service using foreign high-speed trains, called China Railways High Speed or AOA Degree A, was introduced. In 2008, the China opened the Wuhan-Guangzhou high-speed line at 350 km/h, the first line at that speed. Until July 2011, when the maximum speed was lowered to 300 km/h, it was the fastest line in the world. As of 2011, China has the world's longest high-speed rail network with 8,358 km of route. The network is still rapidly expanding to create the 4+4 national high-speed rail grid by 2015. On December 25, 2012, China opened the world's longest high-speed rail line, which runs 2,208 km from the country's capital Beijing in the north to Shenzhen on the southern coast. On December 26, 2012, the world's longest high-speed line opened in China. The Beijing-Guangzhou-Shenzhen Hong Kong high-speed railway at 2,298 km. Taiwan. Taiwan High-Speed Rail's first and only HSA line opened for service on January 5, 2007, using Japanese trains with a top speed of 300 km/h. The service runs 345 km from Taipei Railway Station to Xinzhuang Station in as little as 96 minutes. Once THSA began operations, almost all passengers switched from airlines flying parallel routes while road traffic was also reduced. Introduction into Near East Middle East. In 2009, Turkey inaugurated a high-speed service between Ankara and Eskişehir, becoming the first rail line outside East Asia and Europe to operate a regular high-speed passenger rail service. This has been followed up by Ankara-Konya line. Besides Turkey, Saudi Arabia is also in an advanced stage of project completion for their HSA line, due for revenue service in 2016. Network. Maps. Technologies, dedicated tracks. As defined by Europe and UIC, generally the high-speed rail is a set including a high-speed rolling stock and a dedicated high-speed line. Japan was the first nation to build a totally new and dedicated lines and network for its Shinkansen. It was followed by France, then Germany, Spain, etc. Most countries today with high-speed rail have dedicated high-speed tracks. Notable exceptions are the USA and Russia. In certain cases, in particular in England in the 1970s for the HST, and in China recently, classic old lines have been upgraded to support new high-speed trains, often up to 200 km/h. For unconventional trains, such as or copyright road trains and maglev, the use of viaduct dedicated tracks is necessary. Tracks design. Continuous welded rail is generally used to reduce track vibrations and misalignment. Almost all high-speed lines are electrically driven via overhead cables, have in-cab signaling, and use advanced switches using very low entry and fog angles. Constrictions, such as at grade crossings, where lines intersect other lines and/or roadways, are eliminated. For this reason, Japan and China typically build their high-speed lines on elevated viaducts. High-speed lines avoid tight curves, which reduce speed. Curve radius is typically above 4.5 km, and for lines supporting 350 km/h speeds, typically at 7 to 9 km. The lines may rest on traditional sleeper and ballast or on concrete tiles, and fences prevent access to the tracks on foot. Road rail parallel layout. Road rail parallel layout uses land beside highways for railway lines. Examples include Paris Lyon and Car Paragraph LN, Frankfurt, in which 15% and 70% of the track runs beside highways, respectively. Track sharing. High-speed lines may be exclusive or open to standard speed trains. In France, high-speed lines use standard gauge like the rest of the network, but are used only by passenger TGV, and by the postal TGV. In Germany, high-speed lines are shared between ICE, international high-speed trains, regional trains and freight trains. In China, high-speed lines at speeds between 200 and 250 km/h may carry freight or passengers, Lines operating at speeds of 300 km per hour are used only by passenger CRH trains. In Japan and Spain, high-speed lines use standard gauge as opposed to the rest of their respective networks and are thus dedicated to high-speed trains. Sharing a line between fast and slow traffic reduces its maximum carrying capacity by a very large factor, by forcing much longer intervals between trains at the two different speeds. Construction costs. Japanese systems are often more expensive than their counterparts, because they run on dedicated elevated guideways, avoid traffic crossings and incorporate disaster monitoring systems. The largest part of Japan's cost is for boring tunnels through mountains, as was also true in Taiwan. In France, the cost of construction for LGV estate is minimized by adopting steeper grades rather than building tunnels and viaducts. However, in mountainous Switzerland, tunnels are inevitable. Because the lines are dedicated to passengers, gradients of 3.5%, rather than the previous maximum of euro 1.5% for mixed traffic, are used. More expensive land may be required in order to minimize curves. This increases speed, reduces construction costs and lowers operating and maintenance costs. In other countries, high-speed rail was built without those economies so that the railway can also support other traffic, such as freight. Experience has shown, however, that running trains of significantly different speeds on one line substantially decreases capacity. As a result, mixed traffic lines usually reserve daytime for high-speed trains and run freight at night. Rolling stock. Key technologies include tilting train sets, aerodynamic designs, air brakes, regenerative braking, engine technology and dynamic weight shifting. Comparison with other modes of transport. Optimal distance. While commercial high-speed trains have lower maximum speeds than jet aircraft, they offer shorter total trip times than air travel for short distances. They typically connect city center rail stations to each other, while air transport connects airports that are typically farther from city centers. High-speed rail is best suited for journeys of 1 to 4.5 hours, for which the train can beat air and car trip time. For trips under about 700 km, the process of checking in and going through airport security, as well as traveling to and from the airport, makes the total air journey time equal to or slower than HSR. European authorities treat HSR as competitive with passenger air for HSR trips under 4.5 hours. HSR eliminated most air transport from between Paris-Brussels, Cologne-Frankfurt, Madrid-Barcelona, Nanjing-Wuhan, Chongqing-Xi'an, Tokyo-Nagoya, Tokyo-Sendai and Tokyo-Niigata. China Southern Airlines, China's largest airline, expects the construction of China's high-speed railway network to impact 25% of its route network in the coming years. Market shares. European data indicate that air traffic is more sensitive than road traffic to competition from HSR, at least on journeys of 400 km and more perhaps because cars and buses are far more flexible than planes. TGV Sudist reduced the travel time per Euro line from almost 4 to about 2 hours. Market share rose from 40 to 72%. Air and road market shares shrunk from 31 to 7% and from 29 to 21%, respectively. On the Madrid-Euro-Sevilla link, the AVE connection increased share from 16 to 52%. Air traffic shrunk from 40 to 13%. Road traffic from 44 to 36%, hence the rail market amounted to 80% of combined rail and air traffic. This figure increased to 89% in 2009, according to Spanish rail operator RENFE. According to Peter Joe Rietzma, the rail market share S, as compared to planes, can be computed approximately as a function of the traveling time in minutes T by the formula. According to this formula, a journey time of 3 hours yields 65% market share. However, market shares are also influenced by ticket prices. Energy efficiency. Travel by rail is more competitive in areas of higher population density or where gasoline is expensive, because conventional trains are more fuel efficient than cars when ridership is high, similar to other forms of mass transit. Very few high-speed trains consume diesel or other fossil fuels, but the power stations that provide electric trains with power can consume fossil fuels. In Japan and France, with very extensive high-speed rail networks, a large proportion of electricity comes from nuclear power. On the Eurostar, which primarily runs off the French grid, emissions from traveling by train from London to Paris are 90% lower than by flying. Even using electricity generated from coal or oil, high-speed trains are significantly more fuel-efficient per passenger per kilometer traveled than the typical automobile because of economies of scale and generator technology as well as lower air friction at the same speed. Rail networks, like highways, require large fixed capital investments and thus require a blend of high density and government investment to be competitive against existing capital infrastructure. Automobiles and buses, high-speed rail can accommodate more passengers at far higher speeds than automobiles. Generally, the longer the journey, the better the time advantage of rail over road if going to the same destination. However, high-speed rail can be competitive with cars on shorter distances, 150 km, for example for commuting, given road congestion or expensive parking fees. Moreover, typical passenger rail carries 2.83 times as many passengers per hour per meter width as a road. A typical capacity is the Eurostar, which provides capacity for 12 trains per hour and 800 passengers per train, totaling 9,600 passengers per hour in each direction. By contrast, the highway capacity manual gives a maximum capacity of 2,250 passenger cars per hour per lane, excluding other vehicles. Assuming an average vehicle occupancy of 1.57 a people. A standard twin-track railway has a typical capacity 13% greater than a 6-lane highway, while requiring only 40% of the land. The Tokaido Shinkansen line in Japan has a much higher ratio. Similarly, commuter roads tend to carry fewer than 1.57 persons per vehicle during commute times. Air travel, although air transit moves at higher speeds, its total time to destination can be increased by check-in, baggage handling, security and boarding. These procedures also adds cost to air travel. Trains are preferred in shorter, mid-range distances since rail stations are typically closer to urban centers than airports. Likewise, air travel needs longer distances to have a speed advantage after accounting for both processing time and travel to the airport. Rail travel also requires less weather dependency than air travel. A well-designed and operated rail system can only be affected by severe weather conditions, such as heavy snow, heavy fog, and major storm. Flights, however, generally face cancellations or delays under less severe conditions. High-speed trains also have comfort advantages, since train passengers are allowed to move freely about the train at any point in the journey. The seats are also less subject to weight restrictions than on planes, and as such may have more padding and legroom. Technology advances such as continuously welded rail have minimized the vibration found on slower railways, while air travel remains affected by turbulence when adverse wind conditions arise. Trains can also accommodate intermediate stops at lower time and energetic costs than planes, though this applies less to HSR than to the slower conventional trains. Safety: HSR is much simpler to control due to its predictable course. High-speed rail systems reduce collisions with automobiles or people, by using non-grade level track and eliminating grade-level crossings. Accidents: notable accidents involving high-speed trains include the following. The 1998 Esched accident. In 1998, after over 30 years of high-speed rail operations worldwide without fatal accidents, the Esched accident occurred in Germany. A poorly designed ICE-1 wheel broke at 200 km/h near Esched, resulting in the derailment and destruction of almost the entire full set of 16 cars and the subsequent death toll of 101 people. The 2011 Wenzhou accident. On July 23, 2011, 13 years after the Esched train accident, a Chinese CRH-2 traveling at 100 km/h collided with a CRH-1 which was stopped on a viaduct in the suburbs of Wenzhou, Zhejiang Province, China. The two trains derailed, and 4 cars fell off the viaduct. 40 people were killed, at least 192 were injured, 12 of which were severe injuries. The disaster led to a number of changes in management and exploitation of high-speed rail in China. Despite the fact that high speed was not a factor in the accident, one of the major changes was the lowering by 50 km per hour of all maximum speeds in China HST, 350 km per hour becoming 300, 250 km per hour becoming 200, and 200 km per hour becoming 160. The 2013 Santiago de Compostela accident. In July 2013, a high-speed train in Spain attempted to round a curve which had a speed limit of 80 km per hour at 190 km per hour, leading to 78 fatalities. Normally high-speed rail has automatic speed limiting restrictions, but this track section is a conventional section and in this case the automatic speed limit was disabled several kilometers before the station. 2 days after the accident, the driver was provisionally charged with homicide by negligence. This is the first accident that occurred with a Spanish high-speed train, but it occurred in a section that was not high speed. Maximum speed. There are several definitions of maximum speed: the maximum speed at which a train is allowed to run by law or policy in daily service, the maximum speed at which an unmodified train is proved to be capable of running, the maximum speed at which specially modified train is proved to be capable of running, absolute speed record, conventional rail. Since the 1955 record, France has nearly continuously held the absolute world speed record. The latest record is held by a SNCF TGV-POS train set, which reached 574.8 km per hour in 2007, on the newly constructed LGV Estate high-speed line. This run was for proof of concept and engineering, not to test normal passenger service. Unlike the conventional records, the TGV records have been made by heavily tuned trains, modified from commercial service trains. Unconventional rail. Speed record for experimental unconventional passenger train was set by the MLX-01 manned magnetic levitation train at 581 km per hour in 2003. The record for rail vehicles is 10,325 km per hour by an unmanned rocket sled by the United States Air Force. Maximum speed in service. Conventional rail. The fastest operating conventional trains are the French TGV-POS, German ICE-3, and Japanese E5 and E6 series Shinkansen with a maximum commercial speed of 320 km per hour, the former two on some French high-speed lines, and the latter on a part of Tohoku Shinkansen line. In Spain, on the Madrid-Barcelona HSL, maximum speed is 310 km per hour. Since July 2011, in China, the maximum speed is officially 300 km per hour, but a 10 km per hour tolerance is accepted, and trains often reach 310 km per hour. Before that, from August 2008 to July 2011, China Railway high-speed trains hold the highest commercial operating speed record with 350 km per hour on some lines. Due to high costs and safety concerns, the top speeds in China were reduced to 300 km per hour on July 1, 2011. Unconventional rail. The Shanghai Maglev train reaches 431 km per hour during its daily service on its 30 km dedicated line, holding the speed record for commercial train service. Markets. The early target areas, identified by France, Japan, Spain, and the US, were between pairs of large cities. In France, this was Paris-Lyon, in Japan, Tokyo-Osaka, in Spain, Madrid-Seville. In European countries, South Korea and Japan, dense networks of city subways and railways provide connections with high-speed rail lines. Asia, China. China has the largest network of high-speed railways in the world, and in 2013 it encompassed 10,000 km of high-speed rail. According to Railway Gazette, the trains between Shijiazhuang and Zhenzhou East have the fastest average operating speed in the world at 283.7 km per hour as of August 2013. Japan. In Japan, intra-city rail daily usage per capita is the highest, with cumulative ridership of 6 billion passengers. Taiwan. Taiwan High-Speed Rail is a high-speed rail line that runs approximately 345 km along the west coast of Taiwan, from the national capital Taipei to the southern city of Kaohsiung. The construction was managed by private company Taiwan High-Speed Rail Corporation at a total cost of the project was $18 billion and this company operates the line. The system is based primarily on Japan's Shinkansen technology. South Korea. Since its opening in 2004, KTX has transferred over 360 million passengers until April 2013, accounting to one South Korean using it 7 times. For any transportation involving travel above 300 km, the KTX secured a market share of 57% over other modes of transport, which is by far the largest. Russia. Other target areas include freight lines, such as the Trans-Siberian Railway in Russia, which would allow 3-day Far East to Europe service for freight, potentially fitting in between the months by ship and hours by air. Americas, United States. The United States has domestic definitions for high-speed rail varying between jurisdictions. The United States Code defines high-speed rail as service is reasonably expected to reach sustained speeds of more than 125 mph. The Federal Railroad Administration uses a definition of top speeds at 110 mph and above. The Congressional Research Service uses the term high-speed rail for speeds up to 150 mph and very high-speed rail for the rail on dedicated tracks with speeds over 150 mph. As of 2013, the Northeast Corridor is the only high-speed rail line in operation in the United States linking Boston, New York City, and Washington, D.C. The California High-Speed Rail project is planned to have its first operating segment between Fresno and Bakersfield in 2021. No other segment is expected to be in service before 2025. Europe. France. Market segmentation has principally focused on the business travel market. The French original focus on business travelers is reflected by the early design of the TGV trains. Pleasure travel was a secondary market. Now many of the French extensions connect with vacation beaches on the Atlantic and Mediterranean, as well as major amusement parks and also the ski resorts in France and Switzerland. Friday evenings are the peak time for TGVs. The system lowered prices on long-distance travel to compete more effectively with air services, and as a result some cities within an hour of Paris by TGV have become commuter communities, increasing the market while restructuring land use. On the Paris-Euro-Line service, the number of passengers grew sufficiently to justify the introduction of double-decker coaches. Later high-speed rail lines, such as the LGV Atlantique, the LGV Estate, and most high-speed lines in France, were designed as feeder routes branching into conventional rail lines, serving a larger number of medium-sized cities. Germany. Germany's first high-speed lines ran north-south, for historical reasons, and later developed east-west after German unification. Italy. During the 1920s and 30s, Italy was one of the first countries to develop the technology for high-speed rail. The country constructed the Diretto railways connecting major cities on dedicated electrified high-speed track and developed the fast ETA 200 train set. After the Second World War and the fall of the fascist regime, interest in high-speed rail dwindled, with the successive governments considering it too costly and developing the tilting pendolino, to run at medium-high speed, on conventional lines, instead. The only exception was the Diretto between Florence and Rome, but it was not conceived to be part of a high-speed line on large scale. A true dedicated high-speed rail network was developed during the 80s and the 1990s, and in 2010 1,000 km of high-speed rail were fully operational. Frecciarossa services are operated with ETR 500 non-tilting trains at 25 kVA, 50 Hz power. The operational speed of the service is of 300 km/h. ETR 1000 train sets are currently under construction and were developed by the consortium formed by Ansaldo Breda and Bombardier. Based on the Bombardier's Efiro train set, it will operate up to 360 km/h on the existing high-speed rail system. Over 100 million passengers used the Frecciarossa from the service introduction and the first months of 2012. Italian high-speed services are recording profits, encouraging Trenitalia to plan major investments and to cede a large part of local and regional services to other operators and focusing efforts on high-speed and long-distance services. Spain. Spain has built an extensive high-speed rail network, 3,100 km, the largest in Europe. It uses standard gauge in opposite to the Iberian gauge used in the most of the national railway network, meaning that the high-speed railways are separated and is almost only high-speed trains, no local trains and no freight. This network is from 2013 connected to the French network, with direct trains Paris-Barcelona. Switzerland. High-speed North-Euro-South freight lines in Switzerland are under construction, avoiding slow mountainous truck traffic, and lowering labor costs. The new lines, in particular the Gotthard-based tunnel, are built for 250 km/h. But the short high-speed parts and the mix with freight will keep the average speeds down. The limited size of the country gives fairly short domestic travel times anyway. Turkey. The Turkish State Railways started building high-speed rail lines in 2003. The first section of the line, between Ankara and Eskişehir, was inaugurated on March 13, 2009. It is a part of the 533 km Istanbul to Ankara high-speed rail line. A subsidiary of Turkish State Railways, Yawan Korteksek +/- Tren is the sole commercial operator of high-speed trains in Turkey. The construction of 3 separate high-speed lines from Ankara to Istanbul, Konya and Sivas, as well as taking an Ankara-Izmir line to the launch stage, form part of the Turkish Ministry of Transport's strategic aims and targets. Turkey plans to construct a network of high-speed lines in the early part of the 21st century, targeting a 1,500 km network of high-speed lines by 2013 and a 10,000 km network by the year 2023. United Kingdom. The UK's fastest high-speed line connects London St Pancras with Brussels and Paris through the Channel Tunnel. It is the only high-speed line in Britain with an operating speed of more than 125 mph. The Great Western Main Line, South Wales Main Line, West Coast Main Line, Midland Main Line, Cross Country Route and East Coast Main Line all have maximum speed limits of 125 mph on all or part of the line. Attempts to increase speeds to 140 mph on both the West Coast Main Line and East Coast Main Line have failed because the trains on those lines do not have cab signalling, which is a legal requirement in the UK for trains to be permitted to operate at speeds greater than 125 mph due to the impracticality of observing line-side signals at such speeds. See also: VAC train, ground effect train, high-speed rail by country, land speed record for rail vehicles, magnetic levitation train, mega project, planned high-speed rail by country, passenger rail terminology, list of high-speed trains, notes and references. Further reading: Cornola Squared, Giovanni. Una leggenda che cor, breve storia dell'ultratreno e dei suoi primati. ETA 200 €, ETA 220 €, ETA 240. Sala Squared ETR. ISBN A88-85068-23-5 De Russ, Jins. Vol 2, Issue 1 inch. In Journal of Benefit Cost Analysis. The BCA of HSR, Should the Government Invest in High-Speed Rail Infrastructure? Berkeley Press, http, Ideas Repco RGBPJV2Y 2011 I1N2 HTML. External links, U.S. High-Speed Rail Association official site, Transrapid Euromaglov, High-Speed in Asia, Japan and Germany, UIC, High-Speed Rail, Tips for Rail Travel Guide from Wiki Voyage.